So in the last class, we discussed about factors and multiples, right? And the definition of factor led us to the understanding of prime and composite number, right? So we discussed what prime numbers are. So prime numbers are the numbers that has only two factors, one in itself. For example, 2, right? And composite numbers are the numbers that has more than two factors. For example, 6. Then we saw how we can compute factors of any given number, right? For instance, if I have 36, how do I find the factors of 36? Right, so we discussed that we should always start from 1 and then ask ourselves, what number should I multiply 1 with to get 36? So basically we are trying to find factor pairs first. So 1 times 36 is 36. Then we move on to 2. Again ask the same question. What number should I multiply 2 with to get 36? It comes out to be 18. So we have another factor pair. Then we find another factor pair. So we check with 3. So we know that if I multiply 3 with 12, I get 36. Then we check with 4, right? So if I multiply 4 with 9, I get 36. Then we check with 5, right? So 36 is not divisible by 5, so 5 is not a possible option. Then we check with 6. So if I multiply 6 with 6, I get 36. Right? Then we check with 7. 36 is not divisible by 7. Then we check with 8. 36 is not divisible by 8. Then we check with 9. So 9 times 4 is 36. Now we notice that we are repeating the same thing. 4 times 9 and 9 times 4. It is the same thing. So we stop computing factors further. So these are the only available factor pairs. Right? So we conclude that once we have this repeated pattern that we observe, then we conclude that we don't have any further factor pairs. Right? And then how do we write the factors? We just arrange the numbers from ascending to descending. For example, the factors of 36 would be 1, 2, 3, 4, 6. Then 6 is repeated, so we'll not go over that again. Then 9, 12, 18, and 36. Right? So if we write the factors, they will be comprising of all of them. But most of the times we are not interested in all the factors. We are only interested in the prime factors. We just need the prime factors. Okay. So if you look at the number, all the numbers, most of them are not prime numbers. For example, 1 is not a prime number, 2 is a prime number, 3 is a prime number. Then you have, other than 2 and 3, none of these are prime numbers. Right? So the only prime numbers of 36 are 2 and 3. Right? So the method that we use to find the factor is known as factorization. So what we did here, it is known as factorization. And the method that we use to find the prime factors is known as prime factorization. Because when we do factorization, we get all the factors of that number. When we do prime factorization, we get only the prime factors. Although there can be a lot of factors, but we just need the prime factors. Right? So that process is known as prime factorization. Okay, and it is very, very helpful when we want to find HCF or LCM of two numbers that we'll study in the later class. Okay, so basically what we are trying to do is we are trying to build the foundations that we want to understand, or that we need to understand HCF and LCM, so that while we study that topic, it becomes very, very easy for us to grasp those concepts. Okay, so to find the factors, we have discussed the approach. We start from 1 and then try to find factor pairs. To find the prime factors, we use factor trees. What are factor trees? Factor tree is a great tool to find all the prime factors of a number. So factor tree is basically a tool that we use to find the prime factors of a number. Right? Here we have mentioned tree. So we consider the number. For example, we had 36, or let it be any number. We consider that as a tree. So 36 is the tree. And then we try to, you already know a tree has a lot of branches, right? We try to split it into a lot of branches. And each branch ends up into factors of 36. Okay, so this is one factor, this is another factor. So these two are factor pairs. So if I start from 2, say, so this will be 18. Right, so this is how we create the branches. And when does the branch stop? Until and unless we reach a prime number. So for example, here I choose 2. So 2 was a prime number. Right, so we'll stop the process because This cannot be divided any further. 18 is not a prime number, so we'll further split this into branches. Right? Again, we'll write 2 times 9. Again, we ended up with a prime factor. Right? Then 9 is not a prime factor, so we'll again split this into 3 and 3. Right? Using factor trees, what we can do, we can represent 36 as a product of just prime numbers. We don't want to represent it as 2 times 18. We just want to represent this as product of prime numbers. For example, 36 would be 2 times 2 times, so 2, 2, 3 and 3. So all the prime numbers. So if you multiply this, you'll get 36. Right, so again, this is just a basic introduction. We'll go into detail in the subsequent classes, then it will be more clear. So we consider this number as the tree. Each branch in the tree is split into factors as we discussed. So this is a tree and we are splitting this into factors. When a factor is a prime number, no new branches are added, as we have seen. So since this was a prime number, we did not add any branch. This was not a prime number, so we had to add branches. Again, this was not a prime number, so we did not add any branch. This was not a prime number, so we had to add branches. And both 3 and 3, they are not prime numbers. They are prime numbers, so we did not add any branches further. Okay. So now let us look at few examples to understand how this works. So for example, we have to find the prime factors of 10, or we have to do the prime factorization of 10. So we build a factor tree. So 10 is the tree and we have to divide it into branches. So this is the first branch and this is the second branch. Right. So the first branch, what essentially we are trying to do, we are trying to find the factor pairs using prime numbers only. Right, so you can take any prime number. For example, you can start with 2 because 2 is the smallest prime number. We are not going to start with 1, and then see what number should I multiply 2 with so that we get 10, which is 5. So 2 5s are 10, right? So 5 is also a prime number and 2 is also a prime number. So I can write 10 as a product of prime numbers as 2 multiplied by 5. So this is the prime factorization of 10. So the prime factors of 10 are 2 and 5. If I ask what are the factors of 10, so the factors of 10 are 1, 2, 5 and 10. So these are the factors of 10, right? But the prime factors of 10 are 2 and 5 only. Okay. Then we look at 30, right? So 30 again we'll have to start with any number. Say if I start with 30, 3, right? We could have also started with 2. We'll see we'll end up again with the same number. So for example, let us do this way. First of all, let us start with 30. Okay, so this is 30. So we can start with 2 first. Okay. Now, what number should I multiply 2 with so that I get 30? So we'll have to divide 30 by 2, so we'll get 15. So this will be 15. 2 is a prime number, so we don't need to go any further. We'll not be creating any further branches. 15 is not a prime number, so we create branch. Right, again we check with 2, so 15 is not divisible by 2, so we'll check with 3. Right, so 15 is divisible by 3, so 3 times 5 is 15. Right, so 30 I can write as product of primes as 30 is equal to, so just find out the points wherein the branches are ending. So 2, 3 and 5. So 2 times 3 times 5. You can check, you'll get the same number as the answer, 30. So 2 3s are 6 and 6 5s are 30. So the prime factors of 30 are 2, 3 and 5, whereas it will have more than 3 factors, right? So if someone says I don't want to start with 2, I want to start with 3. So will I end up in a different answer? The answer is no, you'll end up in the same answer. So for example, if you start with 3, so 3 is a prime factor. So if you multiply 3 with 10, you get 30. Since 3 is a prime factor, we don't need to create any further branch. 10 is not a prime factor, so we'll need to further divide it, right? So when we divide 10, so we get 5 as one of the prime factors and 2 as the other prime factor, right? Again, we'll not create any further branches because all of these are prime factors. So again, we'll get 3, 5 and 2. Earlier, what did we get? 2, 3 and 5. So both are the same. So 3, 5 or 2 or 2, 3, 5. All comprise of the same digits. So the prime factorization will result in 2 times 3 times 5, both ways, or say any other way that you use. Okay. There is one more way in which we can do 30, right? So we'll see that. So instead of writing it as say or starting with 2 or so although I recommend to always start with the smallest number, right? But say someone has some other preference, so they want or say 5 strikes in their mind first if they look 30. So they know that 30 is divisible by 5 and will get a smaller quotient, right? So they'll write just 5, 6 are 30, right? So 5 and 6 here. So 5 is a prime factor. We don't have to extend any further branch. Then 6 is not a prime factor, so we'll extend it further. So 2 3s are 6. Right? 6 we can write as 2 times 3. Both are prime factors. Right? So we'll get again the same thing, 2 times 3 times 5, which is 30. So no matter where we start with, we'll get the same numbers as the factors. Okay. Let us do one more example, 36. Again, we can start from 2 as well. So if I have 36, I can start with 2. So what is the number that I should multiply 2 with to get 36? It is 18, because 18 twos are 36. Then this is the prime number, so we'll stop. This is not a prime number, so we can again divide it. Again, this is also divisible by 2, so we'll do 2 9s are 18, right? Again, this is a prime number, but this is not a prime number. And we know 3 3s are 9, right? So if I have to write 36, I can write 2 times 2 times 3 times 3 as the product of prime factors, right? And the prime factors of 36 are only 2 and 3. Because if we want to, if someone is asking for the prime factors, it is just 2 and 3. Right, we will not write this as 2 comma 2 comma 3 comma 3 because we are repeating the same thing again. Right, but if I have to write it in terms of product, I'll write 2 times 2 times 3 times 3 because 2 times 3 will just give us 6. So I'll have to represent how many times 2 is coming and how many times 3 is coming, such that when I multiply those numbers, I get 36. Okay. Say someone has some other preference to start with 6. So they'll have 6, 6 are 36. Both are not prime numbers, so it will go further. So 6, someone, they'll write it as 3 times 2, and this also they'll write as 3 times 2. All of these are prime factors, so we'll not have to further extend the branch. So the prime factorization of 36 will give us 3 times 2 times 3 times 2, or 2 times 2 and then 3 times 2 times 3. Again, the same answer. So no matter where you start with, you should always have prime factors at the end, right? And if you follow the same process, no matter where you start with, you end up in the same answer. Okay. Similarly, we have 40. Again, we start with 2 times 20 because 2 times 20 is 40. Right? You can try solving this on your own using any other approach. For example, you can take 5 8s are 40. Right? Or say 10 4s are 40. And then see if you end up with the same result or not. Okay, for my case, I'm taking 2 times 20 is 40. Then 2 is a prime factor, so we'll not have to extend this any further. 20 is not a prime factor, so we'll do 4 5s are 20 or say 2 10s are 20, whatever comes to our mind. Right? So here they've mentioned 4 5s are 20. Right? Then 5 is a prime factor, 4 is not a prime factor, so 4 we can decompose it as 2 times 2. So the prime factorization of 40 would give us 2 times 5 times 2 times 2. So 3 times 2 and 1 times 5. right? So this is the prime factorization of 40. Okay.